Design, analysis, and development of improved hollow concrete block making machine. Abstract. This project report deals with the design and development of an improved hollow concrete block making machine. The machine lays a particular number of blocks over the platform and moves further to lay another set of blocks, so as to cover the casting platform, in a continuous casting process. This study attempts to solve the problems encountered on the existing hollow concrete block making machine by improving the design of basic components, increasing production rate and minimizing damages of uncured blocks during transfer. The design is based on data from literature review about concrete and building construction, concrete block machine developmental stage, how concrete block making machine works and manual calculation. To meet the objective based on the design principles, several component mechanisms are improved and analytical design analysis, part drawings, and assembling drawing are also done. Keywords: concrete block, block making machine, mold, compacting vibrating system, tamper. Introduction. The area of interest for this project is how to improve the concrete block making machine to be more productive so the cost of hollow blocks will be reduced. The improved concrete block making machine is smaller in size than the medium concrete block maker, more productive and cost-effective than the conventional single block making machine. It produces about 2,400 standard blocks per day, using 3 to 6 workers, 2 operator and 3 to 4 laborers. The new machine has the advantage of being productive and movable to remote areas for construction. Building of structures from individual units or masonry is one of the oldest forms of construction used by man. The utilitarian hollow concrete block has gained respect in the construction sites since its evolvement. Concrete masonry construction may cost slightly more, but builders and homeowners like its durability, strength, and heat retention qualities. 1. A concrete block is made of concrete that's been molded into the correct shape, and then allowed to harden and cure. Block making machines have been improved on since Harman S. Palmer invented the first successful commercial machinist to make concrete block in 1900, what they are today too. The portable hollow concrete block making machine consists of a steel framework that holds the other components in place. There's a front hopper for pouring wet cement mix, a frame that holds the metal concrete block molds, a tamper for compacting the concrete in the molds, and a mechanism for pushing the molded blocks out of Zemicheal for drying and curing. The machine is equipped with molds appropriate to the recommended hollow blocks to be made. The machine lays a particular number, 4 or 5, of blocks over the platform and moves further manually to lay another set of blocks, so as to cover the casting platform, in a continuous casting process. The concrete block technology is a highly profitable business for micro and small-scale building material producers and construction companies. In Ethiopia, the market for concrete blocks is growing at a rapid rate, especially in the areas where stones and burnt bricks are not easily available or are of poor quality. The focus of this project was to modify the design and development of a hollow concrete block making machine which is smaller in size than the medium automatic machine, movable, cheaper, and yet did not compromise efficiency, and with more production rate and cost effective than the conventional single block making machine. This way more hollow concrete blocks will be made, which will enhance development of the construction. Project objectives. The objective of the project was to solve the problems encountered in the existing concrete block making machine by improving the design of main components, leading to increased productivity. Generally, the target was increase production rate of the hollow concrete block making machine. Minimize damages of uncured blocks during transfer. Minimize power consumption and cost. Make the machine easy and light for manipulating. Reduce foreign currency for importing the machine. Encourage technology transfer in Ethiopia. 2. Design analysis. 1. Description of the improved concrete block making machine. Concrete block technology is based on the principle of densification of a lean concrete mix to make a regular-shaped uniform, high-performance masonry unit. Concrete block technology can be easily adapted to suit special needs of users by modifying design parameters such as mix proportion, water/cement ratio and type of production system. It is an effective means of utilizing wastes generated by stone crushers, quarrying, and stone processing units. The technology has high potential in areas where raw materials are easily available. The market for concrete blocks is growing at a rapid rate, especially in the areas where stones and burnt bricks are not easily available or are of poor quality. Table 4.2 Technical specifications of the machine. Control. Manual. Usable area on pallet. 500 x 912 mm. Maximum block height. 200 mm. Frame dimension, width, height, length. 1100 x 1000 x 1500 mm. Total height of the machine. 1856 mm. Frame weight. 250 kilograms. Material bucket capacity, hopper. 40 LT. Vibrator motor. 2.2 kilowatts, 3 HP. Production capacity per shift, 8 hours. Hollow block, 200 x 200 x 400. 1920. Hollow block, 150 x 200 x 400. 2400. Hollow block, 100 x 200 x 400. 3360. These technical values are based on standard specifications and may vary on customers' requirements, installation type, and location. Capacity value is theoretical value. It may vary according to aggregate structure, operator, weather and accommodation conditions. The vibrations operations mode, eccentric weights attached to the mold, vibrate the mold to provide the proper compaction of the concrete mix. The mold vibrates and produces cyclical sound levels. The vibration mode occurs only when the mix is being molded. As the block leaves the machine, the vibration ceases. Vibration lasts for about 6 sec during each 30 sec cycle. The timing of the cycling is highly dependent on the operating condition and production of the machine. 2. Driving mechanism. The machine uses an electrical motor for compaction purpose through pulley and belt mechanism. 3. Appearance, aesthetic, of the machine. It is good in appearance. Most of the parts are made to appear good for the operator and visitors. The handle arm, the frame, the trolley, the wheel, and the motor stand are designed by taking the appearance of the machine into consideration. Generally, the machine is ergonomically good. See Fig 4.1. 4. Features of the machine. Salient features of the improved machine are given in the following. A portable egg-laying type machine. 4 blocks of size 20 x 20 x 40 cm cast in Oni operation. Output of 200 to 300 blocks in an hour. Better compaction ensured through eccentric weight vibration for consolidation of concrete. 1 motor 3 HP capacity and frequency 50 Hz used for power source. Suitable for casting common concrete blocks and different size hollow blocks. Operators access right up to the molds helps in easy placement of the mix in casting blocks and secreting of concrete mix in the molds while casting hollow concrete blocks. Power required, 2.2 kilowatts. It doesn't use pallets, just lays the blocks on a flat surfaces. After a set of blocks was produced and demolded, the machine moves forward to produce the next set of blocks and leaves the blocks on the floor for curing. It reduces time and energy consumption, because it is almost the same time and energy which is used for producing 1 or 2 blocks at a time to produce 4 or 5 blocks. Amount of damaged blocks is minimized due to the avoidance of pallets and improvement of the sliding mechanisms. The overall size of the machine is minimized by removing unnecessary parts of the existing medium machine like supporter of the tamper, length of the frame, size of hopper and size of tamper trolley guide shaft for easy usage. The arm lever is part of the frame, the design and thus shape of the arm is improved. Now it is simple for handling and manipulating. There is a stopper adjustment bolt for controlling the alignment between the mold and tamper during fitting or mating. Tamper release lever is in place for balanced and easy release of the tamper on both sides. Figure 4.1 The newly designed hollow concrete block making machine. 2. Design analysis of the critical parts. The design was selected from an already made machine in the market with some modification in various parts and section to further enhance the productivity and functionality of the design. The concrete block making machine has a number of components, but this topic focuses on the design of some of components which are critical for proper functioning of machine. The main shaft. The shaft is fixed component of the machine which is normally circular in section that carries the tamper trolley assembly and sometimes including the blank mold. The main shaft of the machine is subjected to bending momentarily. The shaft is supported at both ends and the load is applied at the center. When the shaft is subjected to a bending moment only, then the maximum stress is given by the bending equation, where m equals bending moment, I equals moment of inertia of cross-sectional area of the shaft, SB equals bending stress, and y equals distance from neutral axis to the outermost fiber. So by substituting some values to calculate the diameter of the shaft, first let's calculate the weight applied. Mass of the tamper trolley assembly is about 50 kg on each shaft and the length is 1.2 m. The allowable bending stress is 75 MPa, 75 x 106 n/m2. W equals mxg equals 50 x 9.81 equals 490.5 n. Maximum bending moment at the center of the shaft. Also we know that and d equals 27 mm take 30 mm. Hence, the diameter of the main shaft to be produced is 30 mm. 2. The vibrator compactor system. The main features of the vibrator compactor system were the increased vibration of the die cavity or mold that was achieved through the attachment of an eccentric weight to the compactor drive shaft, CDs. This caused the rotation of thicks to be irregular, and the mold to vibrate excessively as required for sand concrete compacting. The eccentric weight is shown on figure 4.3 attached to CDs. The length of CDs inclusive of pulley is 30 cm. The pulley is connected through a belt drive to a 3 horsepower electric motor which drives the system. The eccentric weight and CDs are made from mild steel material. The diameter and length of the eccentric weight, U, are 6 cm and 11 cm respectively. The diameter and length of the CDs are 3.0 cm and 30 cm respectively. The U and CDs are fastened with a bolt. The two flange ends of the CDs are fitted into bearings housed in a disc. The U and CDs are encased by mild steel sheet. The vibration caused by out-of-balance rotation when the U and CDs rotate is transmitted to the long face of the mold of the machine. The block mold was fabricated from a mild steel sheet of thickness 3 mm. The block mold is rest in the ground when the machine is being operated. Mild steel frames are used to secure the block mold firmly in position in all its sides. The block mold is designed to move upwards along the inside of the frame to facilitate the ejection of molded block. A lever or arm is attached for ejecting the molded blocks. A. Theoretical analysis of the compacting, vibrating, system. The principle of the concrete, vibrator compactor, block making machine is the eccentric weight. The eccentric weight, based on calculation for size, was fastened on the compactor drive shaft, CDs. The CDs was also based on design as carried out below. The attachment of eccentric to CDs caused an out-of-balance rotation that sets the long face of the mold to vibrate, a process which compacted the wet block mix. A. B. The rotation of the shaft gave rise to centrifugal force, FC, which acted radially outwards in a direction that is perpendicular to the axis of rotation of the compactor drive shaft, and through the center of gravity, G. Centripetal force is defined as a force that pulls a rotating or spinning object toward a center or axis. Encarta dictionary. According to Newton's third law of motion, every action must have a reaction. Therefore the reaction to centripetal force is called centrifugal force. 6. Centrifugal force is defined as the force that pulls an object away from the center point. However, since an object would only move tangentially away from the center on a linear path, force of velocity, and not continue around a center point, centrifugal force is actually not a force at all, but rather a concept that represents an effect. Some definitions even describe this as an imagined force. This is interesting to keep in mind when applying these ideas to vibrator compactor system. The centripetal force Fp was equal to Fc but in the opposite direction towards the center of rotation. There were 4 forces that were relevant in design of the vibrator compactor system of the machine. They were the centrifugal force, Fc, the spring force, Fs, the force due to flexural rigidity, Ff, and the force due to the wet block mix, Fwb. The point O, Fig 4.4, was the geometric center of the eccentric weight, G was the center of gravity of the CDs and eccentric, μ was mass of eccentric, Mwb was mass of wet block mix, y1 was the length OD and was the additional deflection of the center of the CDs when it rotated it. Rad/s, E was the length OG which was the initial distance of the center of the eccentric from the combined center of gravity of the CDs and eccentric weight, K was the stiffness of CDs, it is the ability of a material to resist deformation under stress. The modulus of elasticity is the measure of stiffness, EI was the flexural rigidity of the CDs, E was the Young's modulus of the CDs. Was the moment of inertia of the CDs, Ls was taken as the length of the compactor drive shaft, Le as the length of the eccentric, Y2 was half the diameter of CDs and line of action of the flexural rigidity and G as acceleration due to gravity. The design required that the following quantities were known. 1. The forces activated in the system. 2. The mass of the CDs and eccentric. 3. Force due to wet block Fwb. 4. Operating stress. 5. The diameter of the CDs and eccentric. 6. The length of the CDs and eccentric. 7. The lengths of Y and E for the CDs and eccentric. B. Forces activated in the compacting vibrating system. These were found to be 4 in number. I. The centrifugal force due to the CDs and the eccentric weight Fc, which was stated in Fc equals μ. 2. Y1 plus E, 1. Where μ, Y1, and E are as stated above, Fc acted away from the axial center of the CDs perpendicularly. 2. The spring force in the CDs, Fs it is given in 2. Where K is the stiffness of CDs. 3. The force due to the flexural rigidity of the CDs, Ff the quotient for Ff is given as where K, E, I, L and Y2 are stated above. 4. The force due to the wet block mix, Fwb, and is given as where Mwb and G are as defined above. C. The mass of the eccentric and CDs. A 2.2 HP 3-phase electric motor, which ran at 2,840 rpm was selected because it was available in the market. The speed of rotation of motor. For vibration to be propagated continuously, the eccentricity ratio was maintained at Y1/E1. Also for the equilibrium, equation, 1, and 2, were equal, i.e. K, stiffness, equals 31,000 N/m for mild steel. For calculated values of μ were 0.21, 0.23, 0.25, 0.26, and 0.28 kg respectively. Selection of μ equals 0.21, 0.23, and did not give as adequate a vibration response as did 0.26. The bolt and nut which fastened the eccentric weight to the CDs, increased μ to 0.50 kg. The weight of the CDs was a half that of eccentric by design, i.e. d. Force due to wet block, Fwb. This is given in, Fwb equals Mwb x gx. 1 dry 20 x 20 x 40 km block equals 17 kg, and the mass of 4 blocks will be distributed to the 3 eccentric weights in the CDs. Fwb equals 101.6 kg x 9.81 x 0.4 equals 398.6 N, with wet block being 20% heavier than dry block including weight of the MOULD 20 kg and equals 0.3-0.7 select 0.4. E. Operating stress, S. This is given in F. Diameter of eccentric weight and compactor drive shaft, CDs. The CDs carried the weight of the wet block mix in bending under minimum tension with a combined shock and fatigue factor of 1.54. The drive torque, T, was given in. For the 3 HP motor which ran at 2840 rpm and P equals 2.2 kilowatts. T equals 7.4 Nm. The CDs in bending was expressed as MWBXGXXRs, x 1.5 equals 7.4 Nm, 6. Where Rs equals radius of CDs. Shows Rs equals 0.0125 m. For the eccentric weight, the radius was calculated as where Re is the radius of eccentric weight, given wet block mix as 20% heavier than dry brick of weight 81.6 kilograms. Shows Re equals 0.025 m. Hence, the design diameters of the CDs and eccentric weight were 2.5 cm and 5.0 cm respectively. G. Length of compactor drive shaft and eccentric weight. Density of CDs, made from mild steel. I.E. 7. Whereas in LS were area and length of the CDs respectively. Length of eccentric weight LE was H. Length of Y1 and E for CDs and eccentric. For Y1, E equals 3, 1, where Y1 was the length of the center of rotation from the geometric center OD and E was the length of the center of gravity from the geometric center OG. Figure 4.4, the maximum force is assumed to also be 3 times the wet block force as 3. Bearing. Bearings are considered to be the most critical components of machinery. From specification description and standard table for 25 mm diameter shaft bearing the basic load rating, 4th medium series ball bearings the design life is 5 years and design life hour is 10,000 HR. From table, the required value where C equals basic load rating, N, P equals equivalent radial load, N, and FR equals radial load. Then the required basic load rating, C, equals, C/P, P, for radial load only. P equals FR, so P equals 1195.8 N from the compactor vibrator design part. Basic load rating. And the bearing number 305 having C equals 12.5 knots, is selected. That means the bearing is of medium series whose bore is 0.5 times 5, i.e., 25 mm, outside diameter equals 62 mm and width equals 17 mm. 4. Pulley. The dimensions for the standard V-grooved pulley, refer Fig 4.11, are shown in standard tables, from which we find that for A-type belt, W equals 11 mm, D equals 12 mm, A equals 3.3 mm, C equals 8.7 mm, F equals 10 mm, and E equals 15 mm, 2 equals 34. Figure 4.11 cross-section of a V-grooved pulley 4. We know that face width of the pulley B equals N1, E plus 2F equals 2,1, 15 plus 2 times 10 equals 35 mm. V. Key. A key is a piece of mild steel inserted between the shaft and hub or boss of the pulley to connect these together in order to prevent relative motion between them. It is always inserted parallel to the axis of the shaft. Keys are used as temporary fastenings and are subjected to considerable crushing and shearing stresses. The rectangular key is designed as follows. From data books we find that width of the key, W, equals D/4 equals 34ths equals 7.5 mm. Thickness of the key, T, equals 2W/3 equals D/6 equals 36ths equals 5 mm. In order to find the length of the key to transmit full power off shaft, the shearing strength of the key is equal to the torsional shear strength of the shaft. We know that the shearing strength of key and torsional shear strength of the shaft. From the above equations we have 3. Conclusion and recommendations. The concrete block making machine is designed to produce 4 blocks at a time. It can also produce 5 blocks at a time by changing the mold and tamper assembly to the desired dimension. On the design, in addition to the compacting vibrating system, the weight of the machine is considered in relation to the personnel for moving the machine and ease of operation. The improved machine is suitable for the production of hollow blocks inside of halls and outside, just a leveled concrete floor is needed. It can be fabricated locally and from the accessible materials. The cost of the machine is comparatively low and can be affordable by both poor and rich. It requires little or no frequent maintenance. Generally, the results of this study are optimistic, providing a good starting point for further exploration on the same area. The technology can be easily adapted to suit special needs of users by modifying design parameters such as mix proportion, water/cement ratio and type of production system. In conclusion, the following are recommended to be investigated further. Mechanism to minimize the initial cost for platform concrete. Designing other additional accessories and systems that make the current design to become more ease for operation. Making the machine more ease and simple in relation to ergonomic design. The researchers sincerely wishes that improvement in the concrete block making machine technology in Ethiopia that stepped here to continue and get improved by faculties, students, and other concerned bodies. We are also interested to continue the improvement practice in the future to make it more advanced in compacting, power consumption and production rate. Acknowledgement. The authors would like to acknowledge that some students and instructors at Ottoman Science and Technology University were involved in developing the design, analysis, and development of improved hollow concrete block making machine. The author wished to thank Dr. Mengist Haile Mariam for his invaluable support to this work.